I want to put it on record that what we are about to do today will fully help most of you in your dissertation you are already writing. So if you happen to pay attention, you're going to benefit significantly. Let me see by hands those of you who in your dissertation you have already collected your data for your research. Let me see by hands if you already have your data as we speak. Not some of your data, but all of your data as we speak. How many do we have? Raise your hand and let me see if you have all of your data. Yao and Salasi. Keep your hand up. Don't lower it. Yao, what is your topic about? And how many variables do you have in your data?
Okay, I'm predicting low default.
Good. So your dependent variable is whether or not there is a probability of default, isn't it?
Yeah, for previous applicants.
When you say for previous applicants, you mean for any applicant?
Those that have been captured already, so that I'll train it without them.
You leave the training aside. For you to have probability of default, there must be probability of no default, isn't it?
Yeah.
Yes. So it's not just
a response variable.
I know that. I know that's why we said yes or no. You don't need to use terminologies.
Yes, sir.
Yeah, just pay attention to the substantive matter.
Yes, sir.
You have customers. If the customers are 200, some of them have defaulted, some of them have not defaulted.
Yes, sir.
We want to check the factors that led to the default or the factors that could possibly affect default rate.
Yes, sir.
What factors do you have? How many features do you have?
About 14.
Okay.
So I'm using.
Don't worry. Just answer my question precisely without adding more.
Yes, sir.
Just follow me. Yeah. Now, are you aware this is a binary classification model?
Yes, sir.
And you are clearly aware of the baseline model you will start with?
Yes, sir. Logistic regression, but I'll explore other classification models.
I know. Just that's why I use the word baseline. Follow my question and answer my question. Okay. All right.
Yes, sir.
Now, have you double checked whether or not you have missing variables?
Yes, sir.
Okay. Have you double checked whether you need scaling?
Yes, sir.
Good. Have you double checked whether there are stratifications or groups?
Yes, sir.
Do you have groups or stratifications?
The nature of my data doesn't call for such.
Good. So you don't have stratifications?
No, sir.
Have you decided on the split test percentages you are going to use?
Yes, sir.
Have you applied a split test?
I've been doing simulations. So I've been doing 20, 80, 90, 10, just to see how accuracy and precision of the chosen model will behave.
That is fine.
Yes, sir.
But that is not called simulations. Okay? You are just doing try and error to see the ones you deal with. But that is not called simulation. That is not Monte Carlo simulation, because simulation is deeper than that. All right. So, ladies and gentlemen, most of you are going to be doing most of the things we are going to do, but also I'm going to test you on this as part of your exam. So you might want to take fullest attention. Ahmed God will take you through this bit last time, and he went through 4 different test splits of the data. Do you guys remember using the IRIS data set? Do you remember using the iris data set to go through the splitting of the data?
Yes, Doc.
Okay. I have a couple of questions here to be sure that you guys have understood what has been done so far. Which one comes first? Splitting the data into test and training, or scaling the data? Which one comes first?
Scaling the data.
Which one comes? I want everybody to talk today. Everyone. Raise your hand. Raise your hand. You talk. Raise your hand. You talk. Raise your hand. You talk. Which one comes first? Test splits or the scaling? You know that when you respond to my question, that makes me not move fast. That's how I act. But when you don't respond to my questions, I then move fast and you then get behind, which is not healthy for you. By the way, you should all open your Jupyter notebook for the one I have sent to you in the page. You should have what I am showing here opened. All these questions are to allow you the time to have it opened. All these are to help you have it, because the only way you can better understand what we are doing is to have it opened and be doing what we are doing. All right. So what we are going to start with is we are going to go through the wine data set. The wine data set. Now, this particular wine data set has been cleaned. So I want you to go to this section on your Jupyter notebook, which is back to our white wine data set. In fact, this data set is made up of white wine and a different other wine. However, I decided to just focus on the white wine. Okay. Most of you are already aware of the data set. In fact, last time he even generated this correlogram, the correlation matrix. Did he do that with you?
Yes, please.
Okay, you will get similar thing like this in your exams. You answer a series of questions on it. So take note. You get a series of questions related to a correlation matrix like this. And this correlation matrix is so powerful that you can even submit it in the journal paper, which means you can submit it in your thesis or dissertations. It's packed. When you dump it there, when you do it similar to this and you dump it there, because it's the same code you're going to use to dump it there into your work. Okay, so this was the data set that you dealt with. Okay, the fact that you have a picture of the wine, you are looking at the very latter part of it, which is a white wine. Okay, and according to Lupe, okay, wine is the most healthful and most hygienic of all beverages. A lot of people don't know that. All right, so you have this data set. What is the main target variable? Who can remind us? You looked at it last week. What is the target variable? What is a target variable? Because that would help me to know whether you really did this. What is the target variable? Let me see by hands, those of you who have opened this on your computer screen. Let me see my hands, those of you who have opened this. I'm taking a screenshot. Don't raise your hand when you haven't opened it, because I'll ask you a question you cannot answer if you have not opened it. Now, keep the hand open. Keep the hand raised if you have opened it. When I said that, 4 people reduced their hand, which means they were lying. They have not opened it, and yet they raised their hand. Keep your hand raised if you have opened this document and you have this showing just as mine is showing. And keep the hand raised. Some of you, I will ask you to even show your data set. So don't do it if you have not opened it. Okay. Now keep the hand raised. So I'm going to use these people as evidence so that when they are being given reward for what they have done, you will understand that they are being given reward. See, some of you pay attention a lot when they come here. Class rep, are you here? You have your class reps here. Class rep, unmute yourself and let me know whether you are here. Okay, so I've actually indicated the names of those who have opened the document as at the time I asked for it. And I've put their information out there. So these are the people who are going to be given the necessary 5 marks that I have in store. Every other person will be given negative. So pay attention again, the subsequent ones. Now, what was the feature, the target variable? You can lower your hands now. What was the target variable? This whole thing, data set, what was the target variable? Does it mean that you didn't go through this last time?
So quality.
Have you raised your hand? It's like you're finding it very difficult to raise your hand and talk. Imagine if everybody is talking. You got to participate nicely. Yeah, Cecil.
Quality of wine.
What is the range of that quality of wine? Philip.
0 to 10.
0 to 10. What kind of variable then is it? What kind of variable?
Yeah, ordinal.
It's ordinal variable. Well, not necessarily. Not exactly necessarily. Because it could be anything, but not necessarily ordinal. It could also be what? It could also be what? Say so. Say so, your hand is up. Yao.
Yeah, categorical.
No, that's way out of line.
Nominal.
Pay attention. Don't do lottery here. Could also be what? Some of you are mentioning very strange terminologies. Very strange terminologies. Okay, so this has been used for integers. Okay, this is integers. This is whole numbers. Okay, these are whole numbers. So you can see them as counting variables. Not necessarily floats, but they're counting variables. And therefore, with this, what kind of machine learning model, what sort of, okay, so if you consider this as a binary classification model, then you can now go ahead and use logistic regression. You can use all the decision trees models or any of the ensemble models. But if you consider it as a continuous integer, okay, then you can use any of the basic regressions like OLS, ordinary least squares regression, or lasso regression, or elastic net regression, or ridge regression. You can even go ahead and use support vector regression. Okay, use random forest, use decision trees, neural networks. You know, you can use SGBoost, AdaBoost, CatBoost, you know, Light GBM. You can use all of that in the process. Okay, for this example, we have considered this as an integer. In fact, if you have read the document, you see it here. That is an integer. Okay. It's an integer. But some people have modeled this as classification model. So even between the 0 and 10, you can split between 0, 5 as yes, and then 6, 10 as no, so that you can have classification model. Keep that in mind. But we are going to consider it as an integer, and therefore we're going to use continuous regression. All right. So with this data in mind, I wanted most of you to open the data, and I want to believe that by this time you've opened the data. All the necessary things you're supposed to do with the data, the EDA, the exploratory data analysis, the data pre-processing, everything has been done. Okay. And then you went through the test splits. Now we are going to apply that test split to this very data set. So go to this command here and run the data set and show the head of the data set. Okay. This df.head will give you the head of the data set. I just did that. And you should do a similar one. Can you confirm that you have the same thing that I have here? Look at the quality. The quality is the main target variable. It's on the far right. Okay, you have 666s for the first 5 observations. And then for the first feature, okay, it's the fixed acidity. All of this have been explained in the preamble. Check whether the fixed acidity, the first one is 7 and the second one is 6.3. Can one of you confirm that?
Yes, sir.
Okay. So now let's proceed. This part is easy, so you've all done it. The next part, and the most important part, is splitting the data set. And right now, you know that you can split the data set between training and then test set. One of them is the in sample, the other is the out of sample. Which one is the in sample? Which one is the out of sample? These are questions you're going to get in the exam, so it's very important you are paying attention. Which one is the in sample? Which one is the out of sample? I'm normally not comfortable with if you can talk, I'm normally not comfortable with a lot of typing because I need to toggle between a lot of windows to read your typing. So if you can actually raise your hand and speak, it's more interactive. Imagine I keep typing without talking. Which of them is the in sample and which one is the out of sample? Okay, so use that as a test. Okay, prepare for that. So you have that. Now you have the train, validation, and test set. Most studies will have the train and test set by 80-20 rule, which makes sense. But then you will also have the validation test, which is a microcosm of the training set. So if the training set is 80%, you can take 20% of that 80%, which is 16%, and then the 80% now becomes 64%. And down you have the train, validation, and then finally the test set. Last time, he explained why the validation set is important. You want to look at validation test as a mock exam before the actual exam. Whereas your weekly meeting with your teacher and the weekly, homeworks and all of that become the training set. the validating set becomes the mock exam, and then the test set becomes the exam itself. If you memorize during the homeworks and everything, when it comes to the validation set, you will overfit the data. You will experience overfitting, okay? And therefore, the data will not work well on the unseen data, which is the test set. All right. Now, for this very example, you use this code, you can see that we are dropping the dependent variable or the target variable, okay, the predicted variable, the variable we're going to predict. Okay. But you have the predictors, which are the features. But the predicted, which is the target variable, is not part of the training and test plate. Why? Who can tell me? And you have a question on this as well. Why do you think that you don't need the target variable to be part of the splitting? It's not needed for the splitting. I think he explained it. Told me that he explained it to you last time. And you want to bring your general knowledge, because you will need this in your thesis itself. Not only just what we are doing, but also in your thesis. Why? You can tell us. Why? Yeah.
Because it will correlate with itself, 100% correlation, and it is
Explain what you mean by that.
Okay, so we want to know how the explanatory variables are related to the explained variable, and because it is the target variable, it cannot be part of the explanatory variable unless maybe it's lack variables in the particular model that we are using.
Well, no, I'm not saying that. I'm not saying that it should not be part of the explanatory variable. It's obviously not part of the explanatory variable. It's not. I am saying that doing the splitting, the data splitting, it does not include this target variable, this explained variable, this predicted variable. It doesn't include it. It's not part of it. So when you look at here, at the top here, the quality is the last one, okay? I'm going to split them, and I want to split them, I'll show you. Every variable will be part of the splitting, but then the quality is not part of the splitting, even when you have done the split. And by the way, when I say splitting, if this whole thing, as you know, the sample size is about 3,007. So, oh, it's more than that even. Let's see from it. I mean, remember the sample size. Okay, the sample size observation is quite a lot. Now, let's say that it's 3,000, and then you're going to split it into 80-20. So you have maybe 2,004 and then 600. Okay, so you will have the data split 2,004 and 600. But our focus is not on the dependent variable. It's not on the target variable. It's on the independent variable. It's on the features. And my question is why? Of course, we know that it's not part of the features. But why are we not including it in the splitting process? Why? Because he did that. He did that. He explained. Because if you check your notes, it's there. Okay, where is that? It was given right there with you. I'm only a bit surprised that you don't know. Why was it not part of it? It's here. Why is it not part? Because it's the one you're going to influence. Why is it not part? That's something he has already told you. Or he didn't teach you. Maybe he didn't, right? He didn't, right? Did he? The thing is that you can't even confirm for me whether he did or he did not. Anyway, so I'll give you that again as your assignment. Prepare for that. Normally, I like one of you to say it and even be wrong. Then I can explain it better for you because you tried to explain it to be wrong. So let's move on. Now, we're going to do a splitting. So X is all the features and Y is that of the target variable. Okay. So we are using 64% for the training set, 16% for the validation. Okay. And watch this. The first split is going to be split them between 80 and 20. So this first command here will split them between 80 and 20. So watch it. We have renamed the X variable, that is the independent factors, as X train. X train. Okay. And then X val, X train val, and then X test. So you have the independent factors or the features being split into, train validation put together, and then test sets for the S variable. That is for the features. Then we'll do the same thing for the Y. That is here. So Y train validation and then Y test. Okay. We use this command called train test split to do that. The test size is 0.2, which is 20% for the test. Which means that automatically the 80% is for the train val or the training validation set. Then after that, we put away the test set. Remember, the test set is 20%, so we leave that. Then you come to the second split. Watch the second split. It is X train, is no longer X train val. It is that X train val, now you are splitting it into training and validation. So you have X train and then the X validation. And then when it comes to the dependent variable, the target variable, you have Y train and Y validation. So it is like you now have that 80% and you are splitting the 80% also into two, giving you that 16% and that of the rest. Okay. Now, and then of course, because you are applying the test size to be 0.2 here, 0.2 for the validation set, okay, it means that the other one will be 64. Because the 0.2 of 80% is 16, and 0.2 and 80% of 80% is going to be 64%. And then this final bit will just print the results and allocate the percentages to it. That gives you the following. So with the data set, you have 3,134 samples being 64%, and then 784 samples being the 16%, and then the 20% test set is guaranteed as 908. If you run this thing, it will give you the same number, but the observations may swap. Okay, they may swap because this is a random generation. All right, so you are now able to check that all of them will have the column variable to be 11, and you should do this also with your long essay, with your dissertation. Now I decided to just show you how the train validation set will look like. So this is a train validation set. This is just a sample of it. Okay. Remember, the train validation set is just the addition of the 3134 plus the 784. That is a train validation. Okay. Now, if I go and do just the test alone, okay, which is a 20%, I just want to do that. You see, the 20% is just 980 rows. That's what you see down here, 980 rows. But then the train validation is different. Now, suppose I do the val, the validation set alone. That one was 16%. Okay, so just change this one to val. It will give you the 784 observations. And watch it carefully. You see that in all of these, the far right, there is no quality variable for the target. There is no target variable because that is not a focus here. All right. So we now prepare the data set for the modeling. Now, this is an important point. One of you said that you are doing loan default prediction. Most loan default predictions have imbalanced data. What is an imbalanced data? Does anybody have an idea? What is an imbalanced data? Yeah.
So the two classes are not equal or at par. There is a significant variance between the two classes.
Give an example of an imbalanced data.
So if we have a 10,000 total sample, then maybe yes will have about 6,000 and no will have about 4,000.
That one is not even too much imbalance, right?
Yeah.
Maybe 90% and 10%.
Okay. That's right.
That's more stronger. And most loan default data are like that. In fact, not just loan default. Some of you are predicting stock price, gold price, silver price, platinum price, palladium price. You know, most binary classification models will have that. And so you got to really, really be careful to be able to use stratification to preserve the class ratios. What does that mean? If there are imbalances, then it means that if there are groups, you got to make sure that each of the imbalance and each of the splitting will have a portion of the group. So if it is 90% against 10%, okay, and there are groups within, let's say we are talking about customers who have defaulted, and most of these customers who are defaulted, you have classified them to between the southern region, the middle region, and the northern region. Then you got to make sure that the same proportion of the southern region guys are in the 90%. Okay, the same proportion are in the same proportion of the middle region and that of the northern region are also in that 90%. And the same proportion for each one is also in the 10%. So you are classifying, you are letting the splitting contain the classes equally. That is if you have an imbalances. Okay? And if you do that, if you have that, this is what you are going to have here. Okay? This is what you are going to have here. Well, we'll check whether our own is, but it doesn't. It doesn't. So leave that. But if it does, this is the code you're going to use for that paper. I didn't run that code. Okay, so once you're done with the splitting of the data set into training, validation, and set, and again, you can remove the validation and you just have training and test. Okay. Once you're done with that, you now go into scaling. You scale the data set. Scaling simply means that you are normalizing or standardizing. You are normalizing or standardizing. Now, when do you use normalization? I've given you the point clearly here. Okay. You use normalization, which means you are using minimax approach to be able to handle the thing. And you use standardization is basically, you know, using the Z value to standardize. We used to do this thing a lot. Okay. When there is anything that is not in the standard scale, you use Z equals to X bar minus mu over the sigma or over the S. Okay. That becomes the standard deviation or the variance, whichever one you are working with. So this is it. So you can convert a random X variable into a Z variable. Now, why do you do that? Very, very simply. Some of the variables are too big. Some of them are too small. Okay, that's why you got to standardize or scale the data. So there are several reasons why. I gave a couple of examples, and you get some of this in your exam. Okay. For example, when the features have got different scales. So we have an example here. When you take alcohol content is between 8 to 15%. Sugar content is between 0 to 20 plus GL. And the pH factor is between 2 to 4. So different scales. Okay. So that different scales can cause issues when you're optimizing the algorithm. For example, take sulfur dioxide. Let's go up here. Look at sulfur dioxide, total sulfur dioxide. The values are 135, 99, 173. Big. Most of them are above 100. Now take the chlorides. Okay. This is sulfur dioxide. Now take the chlorides. Look at it. They are not even up to 1. Majority of them are not even up to 1. They are not even up to 0.1. Many of them are 0.0 something. So what does that mean? It means that you're going to now have this variable in higher scales of above 100 and the chlorides variable in lower scales of below 0.1, 0.01. Okay. Such mismatch will require that you bring all of them into a similar scale. That is the main thing about scaling. Now, when you are doing regularized regression, which we shall look at very soon, which are the ridge, the lasso, and the elastic net, you have done this. Your lecturer told me that he has taught you all of this, unless you can confirm otherwise. Okay, so when you are doing those things, it's very important to scale. Very, very crucial to scale. Okay. Because these guys will have something we call penalty terms. And the penalty terms will treat all the coefficients equally. So if the variables are not equally scaled, then there's a problem. So without scaling, the features with the larger scales, like the sulfur dioxide, the one you have here, total sulfur dioxide, it has larger scale. Compare with those with the lower scales like chlorides. The larger scales guy will be punished, less relative to the effect of their effect on the quality of wine. So there are several ways you can handle that. Another thing is some of the regressions or the algorithm, they use something we call gradient descent, which converges faster. It's also more dependable when the features are on similar scales. So if you are going to use anything related to gradient-based optimization, scaling is warranted. And in fact, if you are doing scaling, justify to the reader why you are scaling. Make your work beautiful. I've invited some people here. There are some students who have joined you from other universities, okay, who are enjoying this thing because they needed to understand this thing to be able to proceed with their research. Okay. The next one is feature importance comparison. Okay. If you scale the features, the independent factors, you are able to do meaningful comparison of the magnitude of the coefficient. That is a marginal effect of each independent factor on the dependent. You're able to do that. But it's not all the time you have to do scaling, because if you are using a method like random forest, decision trees, all of them are already scale invariant, which means they don't depend on scale. They do not vary when it comes to scaling, and therefore you don't need that. But when you're doing those regression analysis, you need those scaling. Okay, so the question is that, do you need to scale the target variable? Okay, and the answer is no. You don't need to scale the target variable. Take, for example, the quality of wine is between 0 and 10, okay, which is already in a meaningful scale. They are all in tens, one may say. They are all in ones, let's say that. So it's not that much of a big deal. So we can keep the original scale, and it is cool, it's fine. You can use all the evaluation matrices you can think about. The minimum absolute error, the root mean squared, okay, error, the mean squared error, the mean absolute percentage squared error, all of them, you can keep that. And that is why. Another thing is that the target variable doesn't take part in the gradient descent optimization the way the features will do. So you don't need that scaling. It doesn't affect the optimization speed, okay? Unless a target variable is really having big differences. That's why we have an example here. If the target variable has got very big, in the case of this wine, it's not likely. I've already given you the numbers. It's not likely. Suppose one particular wine rating is 100,000 and the other rating is 0.001. Now the gap is too much. And in such a case, you have to do what? Your scaling. You have to do your scaling, but then not. Okay, so now we are not going to do scaling, but if we were scaling, and I'm talking about the target variable, if we have to scale, and we are going to scale for the other ones, the features, this is the formula we are going to use. We are using the normalization. Why? Because, like I said, we are doing a regression. We are considering the variable as an integer continuous variable. So we are doing a regression. How do you do the scaling? Or there's something in Python known as the standard scaler. That's what you use. So the first thing to do is to create the scalar, okay, create a standard scalar object, which is called scalar here. And then you take the entire data frame and then scale all the X train. Remember, at this stage, you have split them already. And the split actually gave us X train for the training set. Okay. And then, and note that you are doing it for the dependent variable alone. So you do a scaling of the training set. And then, of course, if you are doing validation, you also do a scaling of the validation set. And if you are doing a test set, you also do a scaling of the test set. So you will have X train scaled, X val scaled, and then X test scaled for each one of them. Please remember that if you are not doing the validation, you don't need to worry yourself with these things. You can remove the validation part and then proceed. You can, if you use my coding, even for yours, and just use the same data set and proceed, it will work perfectly, even for your thesis. It doesn't matter whichever one of you is doing this. Okay. Now, once you've done the scaling, unless you have a question, well, once you've done the scaling, now you can proceed to do your modeling. I will ask you questions about this scaling. So I hope and pray that you have understood how this scaling is done and why you have to do it and why we don't need to do for the dependent. All right, now we are ready to do modeling. This is the part where you see most of you will have research objectives. Now, Yao, you were the one who were talking. Was it you with your topic? Who was talking about his or her topic?
It's me, sir.
It's you.
Yes, sir.
Okay, good. How many how many objectives do you have?
I have 3.
Good. What's your first objective?
I'm exploring the recent machine learning models that are used for loan prediction. Then I'll look at.
Wait, no, hold on. So that's your first objective.
Yes.
You are exploring them.
Yeah.
You don't know which one, you are exploring them, isn't it? You don't know which one. I think we've lost him. Who can discuss his or her objective with me? Look, if you discuss your objective with me, it's going to help you to shape your work. It's going to help you now yourself. So take advantage of opening up to discuss your objective.
Yes, sir.
You're back, eh?
Yeah.
Looks like you're the only serious one here. Okay. Right. So now your objective, you're going to explore. Of course, it will start with the word to explore, isn't it?
Yes, sir.
Yeah.
Then I'll use accuracy and precision, the model that will give me the highest performing statistics. Then I'll write the methodology to support that one. So that will be the choosing model.
Yeah. So how many machine learning models are you looking at to be able to determine which is the most efficient?
For now, I've explored about 6, and I think neural network is giving an indication that it is going to be the most promising one.
Okay. And what were your evaluation metrics that you used?
I was doing precision, accuracy, and area under the curve, but we just did a topic on that from supervised learning. So I'm going to integrate that one too into my work and see which best models my work.
Apart from the logistic, which other approaches did you use?
So logistic, the boots, the ensembles, card boost, a lot of boots. I don't have them off head, but because neural network emerged, I am particular about that one, and I have to learn how the methodology is about that one. But I remember some of the ensembles, the card boost, light boost, and SVM, something like that. Then logistic and artificial neural networks.
I want to believe that in your methodology, you would have written the mathematical model for each one of these. Don't forget that.
Yeah, I explain casually all of them, but for
you got to write a mathematical model for each one.
Yeah, if neural network is chosen, then I have to do justice to that, everything.
For all of them.
From gradient descent to everything around neural network.
For all of them, yeah.
Yes, sir.
Because it's a thesis, it's not even a paper.
Yes, sir.
All right, okay. So we are going to take one of these. Of course, you were looking at binary classifications. Most of you who will be using binary classification will be using similar to what you are doing. But those of you who are using continuous integer variables, like we have here, you are going to use models like OLS, ridge regression, lasso, elastic net, robust, and all of that. Of course, you're not going to use a logistic. You're going to use support vector machine. And I'm sure that the binary classification guys will also use support vector classifier. Okay. Not support vector regression, but support vector classifier. Okay. And then I'm sure some of you will use kernel-based classifiers. And then neural network classifier, all of that. For those that are using binary classifications. But for those of you who are using the continuous, and I'll ask you a series of questions on this, that's what I'm talking about it. For those of you who are using the continuous integer variables, you're going to focus more on these ones on your screen, except the support, except the logistic regression. But even there are more that you have to look at. For example, you have other ones that I have mentioned here. And you got to know advantages and disadvantages of each one. Okay. For example, you're going to use random forest regression. You're going to use even all the gradient boosting, all the 4 different gradient boosting. You're going to use them as well. The key point is I'm going to show you the last time Bernardine, if she's here, she's wondering, hey, are we going to use all of these things? Yes, because the model will just run all at a go. And if you want papers that explains these things, learn one of these papers before you see it in the exam when you are told that write one journal paper that explains these methodologies. Okay, get one of these papers. For example, Cortez paper is published in Decision Support Systems. Okay, it explains that. Yeah, just get a couple of them so that you are aware of it. So let's start with the general linear regression. Every model, you're going to start with the linear regression. And I'm talking about continuous variables. Okay, integer continuous variables, not float. Okay. If you look at this, and in fact, even if it is float, you still use the same linear model. The linear model is provided by this. You have the target variable, which is y, which is influenced by all these factors. In a matrix form, all these individual vectors are put together. Okay. You have individual, column vectors or column matrices are put together, and then you have one big X representing the mama matrix. And then all the beta vectors are put together, so you have one big beta. And then, of course, you have the error term. Now, you can see that I didn't bring the error term here because I'm assuming that this is estimated. So it has a cap. Every item has been explained. And whilst I was talking about the explanation as well. Okay. The reason why I had to use matrix here is because that's what the software is using behind the scenes. The advantages of the baseline regression, linear regression, is that it's easy to interpret and it's quick. Okay. But the problem is that it can experience overfitting. Okay. Especially if there are too many features. Write as many notes as possible because you need this thing in your work. Okay. If there are many features, you will run into the problem of the curse of dimensionality. Write it down. If there are many features, if there are many independent variables, you somersault in the problem of the curse of dimensionality, which means that you have too many features relative to the sample size. You may also have a problem of multicollinearity. Multicollinearity simply means that these features are highly related to each other. So sometimes you have to use the variance inflation factor to check which one is highly inflated. And then you decide whether or not to drop it. You may also use feature selection. You may also have a problem that it has no feature selection. All the features will contribute. So it's like you can't get one that is not contributing. But when you later realize the explainable artificial intelligence method, okay, we call it explainable AI method. There are many of them. Some of them include something we called the Shapley additive explanation. Okay, you also have the line, you have the ALI, you have the PDP. All of these ones improve this approach. And I would encourage you using what's his name? Yeah, you are using logistic regression and other ensembles, right?
Yes, sir.
In neural network.
Yes, sir. Most likely.
And I'm sure you're going to look at feature importance.
Yes, sir. Okay.
And those feature importance, you might want to use one of these explainable AI approaches. It's very easy. I'll show you here. It's very easy.
Okay, sir.
Because it's much better than this part here, this part of the linear regression problem. Okay. And then the other thing is that OLS can be sensitive to outliers. And you can see that if you have the data set like this, okay, and then this very guy here is there, it's an outlier. If the line is supposed to go here, assuming this guy is not there, okay, but now that this guy is there, the line will not go straight away like this. It will rather go this way, which means this guy is driving the line of best fit to itself because this guy is an outlier. It's an outlier. So when there are issues of outliers, the OLS regression model will have an issue. It's not robust. I've spoken about dimensionality issues. It's not robust. Oh, by the way, when there are outliers, then you have a problem of heteroscedasticity and autocorrelation. So the robustness is diminished. Okay. Now, there are several, in machine learning model, there are several linear regression models. The first is the OLS. Watch here, because I will ask you to write some of these models. So pay attention to the model. Let me show you something. The dependent variable that we are looking at in this example, or this practical example, what's the name of the dependent variable? In this wine data, what's the name of the dependent variable? Eves.
So the name is quality of wine.
Good. Wine quality. Okay. Now this wine quality, let's just call it W here. Each of the over 4,000 observations will have a value of wine quality. Now that is called the actual value. Then we have this cap. That is the estimated value, or what is known as the predicted value, or the desired, the fitted, the predicted, the one you're looking for. So let's say the particular wine value is 8, but you expect it to be 10. There's a difference. The difference between 8 and 10 is what? if.
The difference is -2.
And what is that -2 called?
Error
Error. Very good.
or
So now
residual.
the error is now going to be the W minus the W cap here. Now, sometimes this error will be positive. Sometimes this error will be negative. So you may have -2, +1, -4, +3, and so forth. One of the assumptions of the OLS regression is that the mean of these errors should be 0. It's called expected value of the errors, should be 0. Now, these errors, what you do is that you are expecting them to be 0. What the OLS does is that it tries to minimize the sum of the squared errors. So these errors, you know what you have here? Some of them are positive, some of them are negative. So what you decide to do is to square each one of them. When you do that, what happens to the negatives? They move away. Everything becomes positive. So now we are going to have the squared error. And then once you've squared the errors, what do? You sum them. Okay. Now, what the OLS is doing, this sum of this squared error is what is known as the residual sum of squares. The residual sum of squares. Okay. Now pay attention. So we have the residual sum of squares. And that, by the way, is what you are seeing here. So the residual sum of squares is taking the actual, this is the actual, minus, you see the original model is like this. Yi equals to beta naught plus beta, whatever beta it is, let's say beta j, but the j can be as many of them, and then xij. And then of course you have your error. Now, if you have to make the error the subject, what do? You move everything here to the left-hand side. Okay, that's what you do. So when you move everything to the left-hand side, you're going to get yi minus beta naught minus beta j xij. But these are many. Okay, so keep a summation in your mind for them. Okay, and this is actually going to be equal to the error. So that is what you have there. So that's what you can see right here, which is the error now. Now, what do we do with this error? If you can remember, when I square this right-hand side, I'll have to also square this left-hand side. But because this one is many, I have to bring the summation to indicate that there are many of them. And then what you now do is, now you're looking for the beta naught as well as the beta j. Okay. How do you get a beta j? Well, if you look at it carefully, this beta j, the whole thing is like you can minimize. Okay, this whole thing is equal to the error. Okay, I can minimize the error sum of squares. So this RSS, I can minimize it. How do I? I can minimize the whole thing subject to the beta. Sorry, I can minimize the entire sum of this subject to the beta j. I'm not interested in the beta naught because it's just the intercept. You can suppress it. And if you do that, you are going to eventually get something called x prime x to the power -1 x prime y in a matrix form. And that is similar to what you have here. So the final estimated value of the coefficient is going to be this matrix. Now remember, the actual equation has no regularization term, no penalty term. Keep that in mind. It's just y minus beta naught. Okay. So this is the theory behind OLS. OLS is basically minimizing this error sum of squares to be able to find the best coefficient that will minimize the error. And then you can now use that as the key determinant of the target variable, of the dependent variable. It has some assumptions. Linearity is one. In other words, the relationship between the independent factors, the features, and then that of the y must be linear. Independence is like the independent variables should be unrelated to each other. Sometimes we say that they must be orthogonal. So the factors you see here, okay, the factors you see here is like fixed acidity, volatile acidity, citric acid, residual sugar, chloride, free sulfur dioxide, total sulfur dioxide, the density of the wine, the pH of the wine, the sulfate of the wine. All of these are features, and they should not be related with each other. Multicollinearity, that's another name. Okay. Now, the other thing is that there must be no multicollinearity. Predictors are not perfectly correlated. We've said that observations must be independent. Okay, and we also spoke about homoscedasticity. That has to do with errors. In other words, the errors must not be heteroscedastic. They must have constant variance. See, every time you have a random variable like x, this random variable has got two features. One of them is the central tendency, mainly the mean. The other is the deviation from the mean, which is the standard deviation or the variance. Okay. Now, the variance of the errors must be, normally distributed with a zero mean and a constant variance. The errors must be normally distributed with a zero mean and a constant variance. In fact, one way we say this is that we say that the errors, I can use epsilon, I can also use E. The error should be normally, this tilde sign means it should be normally distributed. I can put IID on top of it to indicate that they are independently and identically distributed normally with a zero mean, normally with a zero mean and a constant variance, the variance of 1. Or sometimes the variance, you can just use sigma with an identity matrix. These are theories. And you see, when you are writing your methodology and you bring some of these things, it shows the reader that you know your stuff. Okay? Sometimes when we see some of these things, we cry. Don't cry. Okay? This is master's degree. This is not undergraduate degree. This is master's degree. Okay? And it helps you to know where you are. The advantages of the OLS are all here. Easy statistical theory. See, the theory behind it is strong. That's what I'm talking about. The baseline is good. It's a starting point for everything. And there's no hyperparameter tuning, no tuning. Yes, Eves.
Yes, Doc, I want to know the difference between the marginal effect and the odd ratio.
The odd ratio is used when you are dealing with logistic regression, binary classifications. You never will need it when you are doing with what you are doing. What we are doing is linear regression. You see, logistic regression is not linear. Linear regression is that. Logistic regression is that. Okay. So logistic regression, you'll be using a lot of log ratios, okay, to be able to look at several things, because you have a binary dependent variable, binary classification model. And so you got to take log ratios to be able to make a lot of interpretations. But with a linear regression, you just have beta multiplying the particular independent factor, the feature. This beta, okay, how does it affect the dependent variable, which is the y? So if you have something like y equals to beta naught plus beta 1 x, the question is that x is affecting the y. That's what this equation is saying. X is influencing the y, or x is predicting the y. And this y is not binary. It's not 0 or 1. Binary means it's 0 or 1, 2 options, okay? Like yes or no, reject, accept, male or female. But this y in a linear regression is not like that. It is numbers, 1, 2, 50, 70, 80, 100, and so forth. So in such a case, the beta here is the marginal effect of the independent factor, the marginal effect of the x on the y. We say it's marginal effect. Why? Because if you take the partial derivative alone, dy dx, what are you going to get? You're going to get a beta. Dy dx is going to give you the beta. So beta tells you how much y changes if there is a change in x. how much Y changes. In other words, if Y is internal carbon pricing, sorry, if X is internal carbon pricing and Y is eco-innovation, what you're saying is that to what extent does internal carbon pricing affect eco-innovation? Another example, if Y is your wage and X is your education, okay, you're saying that to what extent does education influence your wage? That beta parameter, that coefficient, once it's estimated, is going to give you the answer. And that is what we call the marginal effect, the marginal contribution of the education on your wage. Yves, do you get it?
Thank you so much. I'm very satisfied.
All right. So that's it. But then OLS has got some issues, outliers, bad performance, overfitting. And as you can see, we call it linear regression, linear. So it means that if your model is exhibiting non-linear relationship, it cannot help you. It cannot help you. But then, hey, for our work, it is a starting point. So let's run the OLS regression. I'm giving you an OLS regression formula, which we use in R software, which we can borrow only for the OLS, only for the OLS. We can borrow and bring it into Python. And this is it. Remember, we have scaled the independent factors, the features. So that entire matrix is called X train scaled. Remember, we are not doing anything with the test set. So if your data set is 5,000 and the training set is 3,003, and then the test set is maybe 2,000, we are not dealing with the test set anywhere here. So watch it. You see that everything is train, 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 train. That's it. We are using the train set. So run this model. So what this code is doing is that we pick up the train set, the training data from the columns that we had before, okay, all the columns above. Then we create a copy of the data set, and that copy, we called it scaled DF, okay? And that scaled DF, we indicate that the Y train, that is the Y from 8, is the quality part. So we now write the formula. The formula is giving us quality is dependent on, you see this symbol, it means it's a tilde sign. It's a Greek letter for tilde. Okay. So this tilde sign means that quality depends on all the X's that have been trained and scaled. All the X's that have been trained and scaled. That is all the features. So you set up the model, and then you call it formula. Then you can now come and import a package known as statsmodel.formula.api as SMF. Use this package or this library, run the OLS model using that library, and then indicate that the formula is what you labeled as formula, and the data set is the scaled one. You fit this model, you print the OLS result, and boom, let me do that. You should do that. Oh, I've jumped something. I know. No. I didn't do the scaling and all of those things here. So probably that's why. But I'm sure you've run yours. So that's it now. Let me see by hand, those of you have done it. Very good. So you run this thing and you should get something like this. Okay. Now, when you look at the R square, look at the R square. What does that tell you? What does that tell you? What does that say? Oh, if you're not answering, you can lower your hand. Luis, what does that R square tell you? The R square is one of the key important factors to check. In fact, you got to be able to explain these things in your work. Okay. Godwin.
So the R square of 0.2 means that the predictors are not able to.
It's 28%.
Yes, 28%. So it means that the predictors are not able to predict well in the model.
Okay, how do you determine that they are not able to predict well? What gave you the confidence they are not able to predict well?
Because of the R square, it should be close to 1. Oh.
Oh, no. There's nothing that says I should be close to 1. I have published papers where the R square is even 11%, and it was still powerful. There is no best R square. The higher is good, but there's no best R square. It is how you argue it.
Okay.
And normally, for you to know that the R square is bad or is not bad, check the adjusted R square. Okay. See, the adjusted R square is close to the R square, which means that there are no irrelevant variables. There are no irrelevant variables. Guys, you got to learn how to interpret the R square. The R square tells you, it's also called a coefficient of determination. Write it down. You see all of this in the exam. It's also called a coefficient of determination. It tells you the variability in the features, in the target variable, should there be any marginal change in all the independent variables, in all the features. So if all the features should behave in a certain way, in percentage terms, how is the target variable going to change? That's the value of the R square. Okay. The bigger the better, but depending on what you're doing, you can say that the R square is acceptable. Sometimes you use a log likelihood, the Akaike information, and the Bayesian criterion. Akaike information criterion and the Bayesian information criterion. This will also help you to be able to determine, the reliability of the model. All of these are telling you about the reliability of the model. That's all. And you'll be surprised very soon. I'm going to show you how powerful this OLS result is compared to the others. Yes, Coco.
So I want to know how to interpret the log likelihood. I see that is minus 3,000.
Yes, you use the absolute value. You use the absolute value. If the absolute value of the log likelihood, the Akaike information, the Bayesian information criteria, if all of them, the absolute values are bigger than 1, there's good news. There's no particular limiting value, just like the R square. See, I used to tell people that R square bigger than 50% is good. But when you look at papers, most papers will even tell you that R square bigger than 10% is very good as well. So as long as the absolute value of these 3 factors, log likelihood, Akaike information, Bayesian, are all positive, that's good. You see the word positive? That's the key. Absolute value. Absolute value.
Thank you so much, Doug.
All right. Now, the other thing is that I think I've spoken about adjusted. The next thing is the p-values for the coefficient. Yes, patience. The p-value. So check the p-value for each of the features.
Doug,
yeah.
please, I just wanted you to take the bit of interpretation on the R squared and adjusted R squared again.
All right. So the R square, in this example, the R square is 28% on average. Okay, 28.2%. So what this means is that 28% of the variation in the quality of white wine, 28% of the variation or the variability in the quality of white wine has been fully explained by all the features. That is the interpretation. 28% of the variation in the quality of white wine has been explained by the entire regression line. 28% has been explained by the entire regression line, which means that there is about 68% that has not been explained by the entire regression line. That's what it means. Now, the adjusted R square should not necessarily be explained. The explanation is mostly on the R square. The adjusted R square is only there to tell you if the adjusted R square is equal to the R square, then it means that there are no irrelevant variables. When I say irrelevant variables, I'm talking about the independent factors, the features. There are no irrelevant features. You see, you are the one who normally will select your features. Some few minutes ago, I was asking Yao, how many features do you have? And Yao said he has 14. I said, okay, he selected his own 14. As to whether they are relevant or because some of the features are irrelevant. And when we go and do the explainable AI approach, you see that they are irrelevant. So what you do is that pick relevant. Now, the adjusted R square would indicate whether what you selected were relevant or irrelevant. If they are irrelevant, the adjusted R square will be way lower than the R square. If they are useless variables. But if they are useful variables, adjusted R square will be exactly equal to the R square, which means what you selected were useful. Does that help?
Yes, Doc. Thank you. Thank you very much.
So look at the independent factors. Look at the features. Take fixed acidity. The value is positive. Okay, the coefficient is positive, which means that there's a positive relationship between fixed acidity and wine quality. Okay, and then you come and check the p-value. Check the p-value. Check the p-value. The p-value should be less than 5% for the relationship to be significant. Write it down. Okay, if the p-value is less than 5%, it means that that particular feature is significant. It's significant in influencing the wine quality. You see, all you got to do is to just write it down, because you will do these things in part of your exams. So it's important you are writing them. Now, so if any of the features has got a p-value less than 5%, it means that that feature, that independent variable, is significant in influencing the dependent factor, in influencing the target variable, which in our case is the wine quality. That is what it means. Somebody raised their hand. I think the person, you can ask a question.
No, it was your last statement answered my question.
All right, okay. So I'm going to ask you, let's look at volatile acidity. Okay, volatile acidity. The relationship between volatile acidity and wine quality, is it positive or negative? And is it significant or insignificant? You can answer. Is it positive or negative? Is it significant or insignificant? Yeah.
It is negatively highly significant.
Very good. It's negatively highly significant. Let's go to citric acid. Citric acid. Who can tell us about citric acid? Is it positive or negative? And is it significant or insignificant? Guys, I will ask you a series of these, so it's important that you are participating. Okay. Emmanuel.
It is positively, but citric acid It's more than 0.5, 0.05, so it's not significant.
Exactly. It is not significant. Let's take residual sugar. Keep some of these answers in your mind. Residual sugar. What are you going to say, Godwin?
So for residual sugar, it is positive and it's significant because 0.0, which is less than 0.5.
Very good. It's positive and so what it means is that the residual sugar is very, very useful to determine the quality of the wine. So if you actually want to know whether your wine is of high quality, it's very important to look at the residual sugar. If you're a manager, you got to check the residual sugar. Okay. Eve says, what can a researcher do if the model satisfied all the assumptions of all the model to be used, but one of the predictors is relevant using different model? There's no problem. Focus on the one that is good. There's no problem to be worried about the one that is, not relevant or relevant. Focus on the one that are relevant. Okay. So for example, all of this, I will not even talk about the ones that are irrelevant unless I want it to be relevant. Let's take, for example, free sulfur dioxide. Is that significant or insignificant? We all know it's positive. Is that significant or insignificant? Free sulfur dioxide. Yeah.
It is significant.
What about total sulfur dioxide?
There isn't enough evidence. It's not significant.
Exactly. And you see, it's even negative.
Yeah.
It's negative. And yeah, the negativity is insignificant. So in this case, you don't talk about it because it's not significant. Now, the last four, are they significant or insignificant? The last four. The last four variables, are they significant or insignificant? Yeah.
They are all significant, sir.
Exactly. Now, if you look at all of these variables, think carefully. Which variable is very, very important in influencing, and keep that in mind. And Bernardine, that comes back to your question, and those of you who are supervised, your question about the Shipley additive explanation, the AI thing. Keep this point in mind. Which variable here would you say is the most significant? Okay, let me put it this way. Which variable here is the most significant variable in significantly changing, let me use that word, changing the white wine quality? Oh, I love this question. I love this question. Which variable is the most significant variable in changing highly the white wine quality, the quality of white wine? Who can give me this answer? Because this is tricky. Most and highly. Explain it in total, yeah.
I would say volatile acidity.
You say volatile acidity?
Yeah, because it has the highest T value. And you said a change. So it could be negative, it could be positive. So maybe if you have to clarify that. But as it stands, the T for volatile acidity is higher than the other one.
That is what you go for. Let's go to Daniel Lamte.
Density, because the coefficient is the highest among the most significant ones.
That is a perfect answer. Okay, guys, it is density here. First of all, you got to take all the highly significant variables, which are 0, p-values of 0, 0, 0, all of them. Those that have the 0, 0, 0, 0, 0. Okay. Now, among them, you check the one with the highest value, whether positive or negative. And when you check carefully, the one with the highest value is density. Keep that in mind. Somebody told me that OLS is bogus. Sure, it is not bogus. Keep that in mind. Density is important. By the way, what is density here? In case you've forgotten, the density that we are looking for The density that we are looking for, okay, in the question, what is that? Okay, the density is a thickness of the wine, the thickness or the non-thickness of the wine. Okay, so that density is the one that is influencing the wine. That is key. And guys, you're going to see something interesting because regression is not a joke. It's a beautiful analysis there, you know, and you see that it's going to translate into the rest. Okay. I just hope that you understand what we just said. This is very important, density here. Now, this is just under the OLS. Now, what about the other things down here? Well, all of them will also talk again about the importance of the model you've done. The skewness, the ketosis, the omnibus, the Western, the Jacobera, and all of these are talking more about. Okay. I will not really bother you much with it, but try and get to know them on your own terms. Now, finally, remember that these variables are telling you about partial significance. Write it down. Each factor, each independent variable, each regressor, each feature is telling you about partial significance. That is individual significance, not joint significance, not joint significance, not joint significance. You see, joint significance has to do with when you combine all of them together, how important are they? I will ask you that question. That's why I'm talking about it. When you combine all these features together, are they significant in influencing the quality of wine? When you combine them, not when you take them individually, but when you combine them. To do that, check the p-value for the F statistic. And once that is approximately 0, using the same principle, you can say that all the independent variables are jointly significant. But if the p-value is bigger than 5%, you will say that all the independent variables are not jointly significant. So now, tell me, would you say that all the independent variables are jointly significant or not jointly significant, and why? Using the p-value for the F statistic, what would you say? What is the value of the p-value for the F statistic? Tell your colleagues, I will take attendance at the end. Tell them, I will take attendance at the end. Daniel.
Yes, Doc. 6.98 exponential minus 271. I would interpret that as less than 0.05.
So it's approximately what value there?
Sorry, come again.
It is approximately what value?
I'll need to do the calculation.
No. Don't go too far.
Okay.
Approximately. What value is
that? 0.
Because you are thinking too much. That's why you say you need to do something. Your colleagues are writing the answers there. You see, all of them got it correct.
Yes, approximately 0.
So that's approximately 0. That's why you said it.
Yes, I was thinking too much, right?
Yeah, you're thinking too much. All right, so that is how you can now determine joint significance. Keep that in mind. Now you can check multicollinearity. Remember I told you that multicollinearity occurs when the features or the independent variables are highly correlated with each other. Okay. And to check whether or not there is multicollinearity, you have to calculate the variance inflation factor for each feature. Each independent variable, check its VIF. Remember, there are 12 variables here. So you check the VIF for each one of them. And you can see clearly that's, and by the way, if the VIF is bigger than 10%, that is serious situation. But I want to put on record that you don't need to touch every VIF. In the machine learning models that we are looking at, they will handle this multicollinearity issue. But I just wanted to know those that, anything that is bigger, like this variable 7, is something to watch out. Okay. 144, 610, these are the ones to probably watch out. But again, they will be corrected in other models. They will be corrected in other models. So sometimes you don't need to worry so much about it. Okay. Which are the variables? 1, 2, 3, 4, 5, 6, 7. So 7 is free sulfur dioxide. Okay. 8 is total sulfur dioxide. So 7 and 8 are causing a problem. Free sulfur dioxide and then the other one. Okay. These two. Free sulfur dioxide and total sulfur dioxide. Free sulfur dioxide is a problem child. The VIF is very big. Okay. When it is above 10, that is when it's below 10, fine. But even for variable 6, I will accept that. But for variable 7 and 8, you got to investigate. But again, the models will handle it. The next models will handle it. Yes, Daniel.
Yes, Doc. So is that right to say that if you have to check the ones that are very problematic, then you have to resort to checking the multicollinearity and no more going back to the coefficients and then the p-values, as in deducing those problematic ones from the interpretation of the p-values and then the coefficients?
No, you cannot, you got to separate them. You got to separate them. So if a variable is good, it's got a very low p-value, low error. By the way, p-value here means the error. Okay, that's the actual error in the research process. If it's got a very low error, it means that that variable is significant in influencing the target variable. Now you go and check its multicollinear factor, and it is what? Big. That's what you're saying, isn't it?
Okay, so what I'm trying to say is from the interpretation of the p-values and the coefficients, can we use just that to deduce which ones are problematic, assuming we are not checking multicollinearity?
When you say, no, you can't use that to check which ones are problematic. Okay. You need to, if you want to know which ones are problematic, remember, they are just telling you importance. They are telling you the significance of each variable, not the problematic. The variable is insignificant doesn't mean that it's problematic. But if you want to check whether it's problematic, go and identify all those that are insignificant, then come and check their multicollinear pairs. Oh, sorry, come and check their VIF here. So for those variables that have got a very high VIF, like these two I've circled, free sulfur dioxide and total sulfur dioxide. Okay, let's go to these two. Okay, these two. Okay. Free sulfur dioxide is significant, and yet it's a very, very high, this thing. It is possible that that is causing a problem. So what you normally do is that you remove free sulfur dioxide and rerun the entire model to see whether the others will look good, and then check the VIF again, the variance inflation factor again. It's possible that the rest will all come low. I'm telling you. I'm telling you. Okay, it's possible that the rest will all come what? Low. So that is one thing you can do. The rest will all come low. Then you know that, free sulfur dioxide was the one that was causing even the others to come low. So it's a kind of a try and error. Remove one from the thing, rerun the model, check the significance as well as the VIF. Okay, that one didn't cause any problem. Put it back, remove the next one, which had a very high VIF, and then check again the significant values as well as the VIFs again. And then you keep doing that. You'll be able to know those that are really problematic. But I'm saying that even if you get those that are problematic, you don't necessarily need to remove them. And why? Because they might still have been part of your literature review. You may have discussed it in your chapter 1 and chapter 2 that this variable is going to be a big issue, or this variable is a variable that you are considering as your important thing in your work. For example, I have one of my students doing loan prediction, and that person is looking at a particular variable, which majority of the studies in the literature hardly look at. And then you go and check that variable. That variable has got a very high VIF. What are you going to do? Are you going to remove it? Hey, no, because you have already written a literature and a whole lot of people who have endorsed the variable. So what you got to do is that maybe it is a model that is not helping. It's an OLS regression model. That's not helping. So you got to use another model. Please, are you getting my point? So you got to exhaust all avenues. And that second model that can solve the multicollinearity issue is the lasso regression. That's it. Lasso.
Yeah, Doc.
Yeah.
Yes, before you move to lasso, if you can go up just a little bit on the VIF, you said that if it is greater than 5 to 10, it indicates high multicollinearity.
Yeah, but let me be flexible. Don't take these things so strictly. Let's take more at if it is greater than 10.
Okay.
Yeah.
Okay, so
the 10, it is even the 10, me, I will not, looking at these numbers I'm seeing on my screen, I will not consider anything below 100 as even an issue.
Exactly. So that's the question I was coming to ask, that if that's the baseline to say the least, then having figures like 600, 144, how do we interpret that?
Yeah, if 100 is a baseline, you see, I picked this 100 baseline from looking at the rest. Then if 100 is a baseline, then 610 is a big issue, right?
Exactly.
But then I can move the bar to 150 so that I will accommodate variable 10.
That's a little bit confusing. So
exactly.
VI,
That's why
does
I'm
it carry
saying
a
that.
standard?
Yeah, there is no
like the p-values
standard. Unfortunately, there's no specific standard. That's what I'm saying. Okay? I'm saying that there is no specific benchmark. The benchmark is there that more than 10. But if you take more than 10, what are you going to do? You're going to remove so many factors, isn't it? Mm-hmm.
Very
You're going
well.
to remove a lot of factors. You will remove almost all of the variables, except some few ones, just 3 left. Then you don't have a story. So what I would have done is that I would have started taking them one by one from the highest. I'll take variable 7. I will remove variable 7 from the model to see whether its removal is doing something to the R square. Its removal is doing something to the significance of the others. And its removal will also bring the multicollinearity VIF scores down for the others. If it doesn't, I put it back. Because the thing is that its removal is not changing anything. So why are you removing it? So you see, I know what you're looking for. You're looking for me to give you a static standard, isn't it?
Yes, Prof, I do understand you now. So I think that it will be on a case-by-case basis, where exactly. When you display the values, then you can then see which ones are highest and how different how far they are from the average of them, and then you can make a decision on that.
All right. Excellent.
Thank you.
Now, under lasso regression, we call it least absolute shrinkage and selection operator. Okay. I'm just going to do lasso regression, hopefully end it there. What a lasso does, and you're going to pay attention to this because there's some questions on this. What a lasso does is that it's also a linear regression, but it uses something we call L1 regularization. what it does is that it shrinks the coefficients to 0. Take note of that word. The coefficients are supposed to be positive or negative in absolute terms or whatever it is. But what this one does is that it brings it to 0. Now, what is it doing? What in your mind is it doing if it brings the coefficients towards 0? Suppose a coefficient now becomes 0. What does that mean? It means that that particular feature is what?
It will be of no effect, sir.
That's it. It's useless. It shouldn't be there. So lasso reduces the coefficient. It doesn't really take it to 0, but it moves it towards 0. Why? Why? Here's the why. Because the one we did before, the OLS, it can bring overfitting. Overfitting is also like the case of dimensionality. Overfitting is when you fit the training data set too closely. What does that mean? Well, let's say that you have some independent variables, some features, and these features are 11 or 14, like the one Yao has, 14. And the sample size is very small. They are like also 15. It means that the dimensions are too many. When I say dimensions, I'm talking about the features. The features are too many relative to the sample size. The sample size must be big. Remember, the law of large numbers is always good. But your sample size is small, and now you have a very plenty number of it. So what is happening here? What is happening here? What is happening is that now you are overfitting. So if there are some predictors or some features, okay, and it doesn't automatically remove those irrelevant variables, then you have this issue about overfitting. It means that some of the variables are useless and you're still keeping them. So lasso comes in there. Papa lasso comes in there and says, Master, the variable is useless and you're still keeping the variable there. So lasso will force that coefficient of that variable to be what value? You can tell me. Lasso will force that variable's coefficient to be what?
To be of no effect.
And by giving the value to be what?
0.
0. So once it gives that value 0, he's telling you that that value was irrelevant and you still kept it. And that's why there has been overfitting. So let me make it 0 for you so that you see that it is useless. It shouldn't have been here in the first place. OLS, you made a big mistake for bringing that variable here. No wonder you have caused overfitting. Now, when you use too many variables, that is what happens. The likelihood is that some of them will be useless. And when that happens, only a few are going to be truly useful. But the thing is that you don't normally know which one is going to be useful. You are only allowing the OLS to automatically select the feature. We call it automatic feature selection. So lasso comes in. It solves this problem. Yes, Joseph.
Prof, I read somewhere that you use lasso regression when the number of features are more than your sample size.
Yes, but that's what I'm saying. That's exactly what I'm saying. That's what I call the case of dimensionality here. But not necessarily when they are more than or. Even when they are equal to, it's still not good. Let's say that the sample size is 30. The variables are 28. It's still not good. The variables are too many.
But Prof, we know that in machine learning, there's no way you can succeed with a sample size about 30. And so I don't know how realistic this assertion applies.
You said there's no way what? Sorry.
You can be successful in running a machine learning model with a sample size of about 30.
Of course. So that is why a
So
sample
I'm just
size is
wondering,
okay.
when I read it, I was a bit confused. I was like, how's that possible that you have your features being more than the sample size? It's not possible. That's what I thought.
No, that is not possible. It's possible, but it's not sensible. It's possible. I'm telling you, I've seen people who are doing research and their sample size is 10. They will tell you that. I just had a guy from South Africa who was doing some thesis and he was dealing with the banks. The banks are only 6. And guess the variables? The variables were 5. In fact, there were 7.
Yeah.
And I told him that you can't go that pathway. Bring it down. He put it to 6. I said, no, bring it down. Then he brought it to 5. That's how far he could go. Because he tells me that the variables, each one is important. I said, oh, good. Now we have to do something we call principal component analysis to be able to determine which one load well. We have to do a lot of things. And even after that, we now have to stretch the sample size. Since the banks are only 6, according to him, now we have to go and increase the sample size so that we can have a lot of observations to counteract, the case of dimensionality.
Yeah.
So yes, Master, you can have it. I'm telling you, you can have it. People do things. So Lasso, you see, Lasso, you just don't know which variable. You see, the guy was telling me that the variables are important. Each one is important. Now, what Lasso will do is that Lasso will prove to you which one is important. It will give some of them 0, telling you that they are not important. So Lasso,
is there a disadvantage with using fewer features?
Yes, there are advantages and there are also disadvantages. We'll look at that very soon. So what a lasso will do is that it will minimize that same residual sum of squares, which we did before for the OLS. But it will augment it by a regularization term called L1 penalty. It will estimate the coefficient by solving the following problem. So you can see that now the beta parameter is beta lasso. Now watch it. The most important thing is this one, because I'm ending with this. The most important thing is that the OLS regression is this part here. Do you realize that? That's the part here. And the lasso adds this term. This term. Look at what it's doing. It is taking each beta parameter. It is multiplying the beta parameter by a certain lambda value and summing it. It is taking, watch carefully, it's taking the absolute value of the beta parameter and is multiplying it by a lambda. You'll get to know what a lambda is very soon. But that is exactly what Lasso is doing. It's multiplying it by a lambda. I was just reading some of the comments some of you are making. Okay. So in a matrix form, this is it. Okay. It is using, everything has been explained actually. The only key thing is the one I just explained, which is the L1 penalty. It's adding that to what the OLS had. This is OLS, and this part added to the OLS is the lasso. Now, let's talk about the regularization parameter. That one is key. What is that? What is that lambda here? It's also a real positive octant. It's a real number. Okay. We call it penalty strength. It tells you how much penalty we impose on the model for having excessively too large coefficients, or better still, too many features. Okay. And of course, these are the terms to explain the information above. These are just the matrix interpretation. And of course, we've already explained that this is the lasso part. The L1 penalty, which is sometimes called L1 norm, or the regularization parameter 1, okay? For every coefficient, remember, it was for every coefficient, okay? And for every estimate, it's the same thing. So if you have independent variable 1, 2, 3, 4, then you will have the regularization parameter, L1 penalty, 1, 2, 3, 4 for each one of them. Each one of them will have a lambda value. Now, the advantage or the key point to note about the lasso is that it will punish large coefficients using this very regularization parameter. Some of the betas are going to be 0, as you can see. Okay. And remember, we said that the OLS fit the data too closely. So this one will relax that fitting. Okay. So it balances the fitness versus the complexity of the model. Because you see, when you use the lasso parameter, you are also making the model complex. In fact, when you even saw it, some of you, it looks like Hebrew. The model looks like Hebrew in your eyes. So there's a bit of complexity. Okay, yes, it will balance that complexity with that overfitting that we saw there. You just need to understand the theory behind the lasso. So what if the lambda is small? Then the L1 penalty is small. It means that, sorry, what if it's large? If it is large, it means that you have imposed a stronger penalty. Okay, so more coefficient will shrink to 0. So if lambda is big, the coefficients are going to come down to 0. It means that you are making them useless. If the lambda is small, okay, it behaves like the normal regression. Okay. In other words, the regularization parameter itself alone falls to 0, and therefore we have a value of the normal regression. So that penalty function goes away. Lasso has some disadvantages. It's not ideal when the features are highly correlated. Okay. It's not. In other words, when there's a lot of multi-collinearity, okay, it will drop some of them. It will drop some of them. But you will later see that ridge regression doesn't do that. Ridge regression will still keep them and will handle that using the penalty function too. Okay. I am more interested in doing, we are not going to run this thing today. We'll run this. Class rep, how many hours do we have? Anybody can answer. Anyway, multicollinearity happens when the predictors are highly correlated. Okay. We know this. We know that multicollinearity happens when the predictors are too close to each other. Now, overfitting happens in high dimensional spaces. I've already said overfitting is when P is the number of features, independent variables, greater than N is the sample size. So when the number of independent variables are bigger than the sample size, we have the issue of overfitting. And that was what your question was, how is that possible? It's possible. Now, when you have large variances in the coefficient, okay, take note. If you check the table I gave you, okay, the table is given like this. The estimate or the coefficient, let me use coefficient. That's what you saw. The coefficient divided by the standard error will give you the t statistic or the t value. And when you read the t value on the table, you get a p value. Now, the standard error, you don't want it to be big. The standard error is actually the square root of the variance. So this point is saying that, this is an interesting point. Okay. If you have large variances, you're going to get large standard errors, and that will make the t value smaller, which will make the p value bigger. And the p value being bigger is not good because you want it to be 0. So the model is going to perform badly on the test data when you later go to the test data. We shall work on the test data as well. So what the ridge regression is going to do is the following. To solve all the above problems, this is what the ridge will do. It will add a penalty term, regularization term, just like the other one, to the OLS loss function, to the OLS residual sum of square function. Is the same thing. And why is it doing that? It will reduce the complexity of the model. It will prevent overfitting by minimizing the following sum of squares. So watch this. What is the difference between this ridge regression parameter and the lasso regression parameter? Who can tell me? This is a regularity. What's the difference between the ridge regression parameter and the lasso regression parameter? There's a simple difference. You can tell me. Joseph.
Okay, so the ridge regression, the
regularization term.
Yes. So if it reduces the coefficient to 0. Mm-hmm. Okay, whereas the lasso reduces or brings it closer to 0.
Okay. But there's something right here, just simple mathematics here that I thought you would have spotted it. What is the difference? Exactly. Eves has given the answer there. Okay, one is having an absolute value and the other is having a square. So if you look at the ridge regression, it's having beta square, but the lasso regression was having absolute value. All of them will break that parameter down by removing the negativity, if it is negative at all. Okay. So here's the thing, the difference. Yes, patience.
Yeah, please, you wanted to know how many minutes we have left.
Yeah.
25.
Okay. So when you look at this, where's that? When you look at this, the regularized regression, the ridge regression, the lambda is positive or 0. That is a regularization parameter. Sometimes we write it as lambda in scikit-learn. So when you use scikit-learn, that's the value it gives. Okay. The intuition behind this whole penalty is this. The ridge regression will minimize the function that we spoke about. And as the lambda value approaches 0, we are in the world of ridge regression. But as the lambda value approaches infinity, then the coefficient will approach 0. But it will never reach 0, but it will approach 0. So understand the two. And the two is that when you have ridge, you can have overfitting. Sorry, when you don't have ridge, okay, and then you have, say, lasso, you will have overfitting. When you have ridge, you're going to punish large values, large coefficients. Ridge is good, but it will punish large coefficients. Lasso will not punish large coefficients, but it will overfit. Ridge is good. It will control the model complexity. Okay. Lasso, because it doesn't control the coefficient, okay, the coefficient may explode, which will now lead to higher variances, higher standard errors, and lower p-values. And when you have ridge regression, okay, those issues are handled. Okay. And because those issues are handled, ridge regression is good to help handle multicollinearity. Okay. So when you have lasso, multicollinearity becomes a bit of an issue. But when you have ridge, multicollinearity is not an issue. The interpretations have all been given here. Okay. But the key point is that the ridge will shrink the coefficient by penalizing them. The lasso will not. Okay. But in the ridge, because it's shrinking the coefficient, okay, it is very good for multicollinearity. Okay. But then the other one, the lasso, is not good for multicollinearity because there's a lot of sparsity in the model. So because of that, both of them have got the advantages. And that's why the final one comes in, which is the elastic net. The elastic net will add both of them. It will take L1 regularization and it will take L2 regularization or L2 penalty, combine the two, and now we have this as an elastic net residual sum of squares. So watch it. It's not difficult at all. So this is a normal OLS regression. Okay. You have the lambda here. It will take the one that is the absolute value, which is the lasso, and then it will take the one that is the square, which is the ridge. It will add all these together and add it to the OLS. And as you can see, it will use log likelihood function to estimate the model. Okay, that's why you have 1 over 2n, and then you have 1 minus alpha over 2n, and so many of those things. You don't need to worry much about it because the software estimates all of them for you easily. So let's get a conclusion of all this, and the good reason why some will also try to use the elastic net regression. The key point is that lambda, which is the regularization parameter, is 0 or positive. That will tell you the overall strength of these coefficients. Okay. Now, if it is equal to 1, then we have pure lasso. Now, I want you to check something here. In here, in the above here, we have renamed the lambda here, but we have also introduced alpha, okay, for the lasso and 1 minus alpha for the ridge. Now, if alpha is equal to 1, then this value here is going to be 1 minus 1, which is 0. So, we're going to have an infinity junction. And if alpha here is 1, then this whole thing is going to be what? In other words, this one is going to go, and then this will also be gone, technically. And so the lambda will be multiplying just it. So we are back to lasso. So that is the point that we indicate that if alpha is 1 here, we are back to lasso. Okay? We have pure lasso. The same way, if alpha is 0, okay, if this one is 0, we are going to have 1 over 2, okay, and this 0, I'm sure you guys can see. If this value is 0, 0 multiply this, so the whole lasso is gone. And we are back to range. So the alpha here is regulating the value between the lasso and then the range. That's why we call it elastic net. The word elastic is like it's taking a hybrid. Okay? If you can remember the price elasticity of demand, okay, there's a kind of a range where it tosses. I wish you could see me dancing here. Where it tosses between left and right, the values there. And elastic net balances those things. So the key conclusion and the features here is that when you have L1 penalty, okay, it will induce sparsity or feature selection. Okay, and that again is a lasso junction. When you have L2 penalty, it will handle the multicollinearity. That is a key thing that you want to be able to keep in mind. And so we balance it. We try and have a bit of both. All of these are used for predicting continuous values. Okay, but the other ones, you can check them depending on what you are doing. All these factors, they can all do a similar thing by improving it. For example, robust regression is resistant to outliers. Partial least squares is used when the features are highly collinear, just like the ridge regression. The least angle regression is a forward-looking method for high-dimensional data. Quantile regression predicts conditional quantiles, not just the mean. GLM extends the OLS to non-normal distribution because it assumes normality, but when the distributions are Poisson, Gamma, Weibull, it can handle that. And then it can also have Bayesian regression for handling uncertainties in the data. After you've run all of this, you can now train the model, the regression model, and then compare and do the evaluation or use the evaluation matrix on the test data to check which one is good. And you are going to also look at a lot of visualizations to do the work. So let's run our model. We're going to run all of them together now. Okay, so let's go here. And now we have about 10 minutes or 15 minutes to do that. So look at this model, which you already have. We are using scikit-learn linear model. We are importing the regression, ridge, lasso, elastic net. I've even included another one, okay, in case you want to handle heteroscedasticity. And then I have indicated that I want you to calculate the mean squared error, the mean absolute error. This mean squared error is the MSE. This one is the MAE. The median absolute error is also here. The maximum error is there. The mean absolute percentage error, the MAPE, is here. The R square, the usual R square we had is here. And then the explained variance is here. I've just included a lot of evaluation matrices. Guys, you can add more. You can add more. Okay, depending on which evaluation matrix you want to use. Okay, what about the model? Bernardine, I told you that when you're doing all of these models, it's not difficult. You see, this command is putting all of them together. Anyway, so this is going to estimate the linear regression. Then the lasso regression, the alpha is 1 here, okay? And then for the ridge regression, we set the alpha to 1. For the lasso regression, we set the alpha to 0.1. Please remember that you can change these alphas. These are hyperparameter tunings. You can alter them, whichever one you like. The elastic net is kind of splitting between the two. So you have the alpha and then you have the L1 regularization. Okay. So the L1 is the lambda. You set that to 0.5. The alpha is 0.1 because it comes from above here. And then I've added the Huber regressor as well. In fact, we should have had more. Okay. But then I've not treated those more, so I can't add more. For example, if you were doing random forest, neural network, you can add all of that. In subsequent ones, I've added all of that. Okay. Now, this method will do the train and splitting. It will do the standard scaling if you haven't already done. So let's assume that we have our variable. We have the X train and X test. I'm just using the X train and X test, okay? I'm just using the 80-20. I'm not doing the validation. Okay. And then I've set the test size to 20%. I'm using the standard scaler because that's for normalization. I'm not using the, I'm using the standardization, not the normalization. And then I've trained my scaled data to this level. I've called it X train. The same thing for the test. I've called it X test scaled. I'll run that. I'll train and evaluate with comprehensive metrics. And these are several things. So this is going to go do all the training here, predict the model, calculate the R square. Now the R square, I have set the calculation formula here. I've also set the adjusted R square formula here. Watch it. N is a Y test, and this is all on the test data. Take note. Test data is the data you didn't use, the unseen data. So this gives you the R square value. This gives you the adjusted R square value. And now I want the results to bring all of the scores. So in the result, I will show the R square, the adjusted R square, the explained variance, the mean squared error, okay, the mean squared error for the test. This is for the train, but also for the test, both test and train. Then the mean absolute error, median absolute error, and then all of the other evaluation matrices. Okay. Now I'll convert the entire data set because I want to create a data frame for everything. I also want to see the coefficient of the results, which is the most important thing. Because you want to compare models. This is what we call the evaluation matrices to select the best. I'll display the entire results in a table form, both for the coefficient as well as for all of them. Let's run that. This is what you get. I'm sure you're also running them. So when you run that, you get this performance matrix sorted by R square. Please remember you can sort it by another evaluation matrix. See? So if you check here, I've indicated that where is the sorting? Okay. I've indicated that we should use the sorted by R square, but I've actually done the sorting here. That I want you to sort the result by R square. So it's going to give me the one with the highest R square first. Now, guess what? This is an OLS. The R square is 27.88. This is a ridge. The R square is 27.88. This is a Huber. This is elastic net in order. So just using the R square, which one is the best? Is OLS. Yeah. Good. Ifs. Using the root mean square, which one is the best? Using the root mean square. So you can check. It will organize all of them. Okay? All of them. Okay? It cannot be lasso because remember the root mean squared is error. Error. So it is still going to be the OLS. So the OLS is the, you see, in all of them is between the OLS and range, if you check it carefully. The OLS and the range have got the same values, generally speaking. Okay. Everything apart from the R square and the adjusted R square, I'll give you something like this to ask you a series of questions. Everything between the R square and the adjusted R square, everything is, the adjusted and the R square are highest. You want more of it. Okay. And then the errors, you want less of them. So if you take, for example, the MAPE, okay, the one with the lowest MAPE is the OLS. So OLS is the best model based on the MAPE, based on almost all the rest. OLS is still the best. Now let's look at the coefficient under each one of them. As for the OLS coefficient, we knew that from the onset. Okay. We knew that density was still greatest. Yes, Emmanuel.
Well, when you look at the map, the Huber has 0.1049.
Good. It's true. So Huber is the best there for the mapping. Yeah, for the mapping. So let me tell you some secrets. So sometimes the tendency will be which one is the best. Normally, the best should generally be supported by all evaluation matrices. Not all, but most of the evaluation matrices. So even though this guy, Huber seems to be doing well, not only with even mapping. Huber is doing well here with the maximum error, with the median error. Huber is still doing well there. Okay. So let's see for the others here. But the R square, Huber is not doing good. Adjusted R square, Huber is not doing good. Let's look at MSE. MSE, Huber is not doing good. RMSE, Huber is not doing good. And the MAE, Huber is at par with the rest. Okay. So again, this is giving some very good clues, but the other things will tell you some other interesting things. So Huber seems to be doing well with OLS, with range. I'll tell you what you should do. Okay. You can visualize the results so that it will give us a better, but just based on the OLS, okay, sorry, based on the R square, we can say that OLS is the best, just based on that alone. But of course, you have to take the others into consideration. This graph, okay, will just do a beautiful analysis for you. So watch it. It will now show you for each one. So this is using the R square. You can see that using the R square, OLS, Ridge, and Huber are all doing great. Using the error metric, the graph will tell you, and you can bring all of this. You should bring all of this in your thesis. Okay. Using the error metric, you can see that the RMSE, MAE, and all of that. You can see that again, OLS is having the lowest error there. Huber is also having some lower error there, okay, as you can see. And then using the MAPE, you can see that Huber is a bit lower than the rest, okay? And then using the maximum error comparison, again, Huber seems to be a bit lower. So you are able to now make a judgment as to which model you're going to select based on that. Okay, I will say that it's always good to take 2 to 4. Let me say that 2 to 4 models to guide you. And then you can check the visualization, the comparison of the independent factors. Now, you remember that we knew that density was the master. We'll come and look at these ones next time. But I just want you to keep something in mind. In terms of negativity here, you see how very long the features are doing, okay, across the coefficients. The values of the coefficient, the direction. In fact, I could have put the numbers on them so that it becomes nicer. But the direction will tell you, for example, when you look at the density, it's negative, but it's moving so wide, okay, so long for these variables. We'll come and talk more about them. And then we'll also talk more about this, because this one is nicer. It's another way of looking at the results for both the test as well as the train. Okay. We'll also look at that next time in our conclusion. And then this is a feature important. This is what we call explainable AI for the Shipley additive explanations. Okay. We'll look at that. And again, you can see that density is doing well. Density is leading. Residual sugar is also very leading. This is what managers want. Okay. And I put the values there for you to see clearly what is happening here. This is the same thing. Again, you can see that density is doing well, followed by residual sugar, followed by alcohol, and before the acidity come in. And then when you go to when you check journals, top journals, they use this graph. This graph again tells you the stretch of the density. We'll look more at it. Density, residual sugar, and then the rest. There might be some slight changes, but you can see that density is consistently the most important variable. And then, in fact, when you look at even the variable in a different graph, okay, again, it shows how powerful density is, you know, in terms of its importance. This is what we call feature importance. We'll talk more about that later. And yeah, so again, some of them might switch between, you know, others, but the key ones will always stand out. Key ones will always stand out. I will look more at the feature importance. Okay, for today, my goal is for you to be able to now know which model is doing well. And you have to take each evaluation metrics to be able to analyze that one. Now, what we've just done here, actually, this is the same thing you would do when you're doing random forest, support vector machine, artificial neural network, convoluted neural network, okay? When you're doing logistic regression, when you're doing, of course, when it comes to binary classifications, there are some few other things you add, you know, like the F1 scores, you know, you look at a lot of the confusion metrics will also guide you in doing those things. Apart from other things, the confusion metrics are the key to use for binary classifications. All right, ladies and gentlemen, that brings us to the end of the entire Moodle.